Hi, this is Cheyenne. Today I'm going to talk about a question related to finding the deflection using the method of integration. So let's see what the question says. For the beam shown below, determine the deflection and rotations at A as well as maximum deflection for portion BC for the beam that's shown using the method of integration, and use I for CD and AB and 2I for BC. So we're going to use I for this portion and 2I for portion BC. I want to find a deflection and rotation at point A as well as a maximum deflection in portion BC. Okay, let's start with our process to solve the problem. So the first step always in the method of integration is to find the reactions. Why? Because we know that from our curvature equations, which we're going to talk about later, we need our moment equation, our general moment equation for each portion. For example, for portion AB, for portion BC, and portion CD, we need our basically general moment equation. But when we are cutting a section, what do we need? We need the force here, right? What's the value of this force? So that's why we have to start our process by finding the reactions. So what can we do? Basically just draw the reactions and just take the moment about one of these points, either B or C. So what I did was just take the moment about point C and just have a convention. And for example, for here I just consider the positive direction as my counterclockwise direction. And if you start, so let's start from the left. I have this distributed load. So I have 10 multiplied by 17, which is the length. So 10 multiplied by 17, what is that? That's force. So this force multiplied by the distance. So what is the distance? Is 12 plus 5 divided by 2, right? So it's 17 divided by 2. Why? Because this force, this distributed load, is equivalent to a concentrated load right in the middle. So because of that, it's 10 times 17, which is 170 for our force, and the distance is 12 plus 5 divided by 2, or 17 divided by 2. And why are we doing all of that? Because it's all about point C, right? It's all about point C. Now we come here, and okay, so I have my inner load here. So actually this is the load I'm trying to find here. So it's going to be By multiplied by 12. And this is clockwise, right? So the moment created by By is By multiplied by 12 about point C, right? And this is clockwise, but my positive sense is counterclockwise. So it's going to be negative. And then another load, so I accounted for the distributed, this force. The moment from this Cy is 0, right? And that's basically the reason we're taking the moment about like point B or C, right? And I have another load here and another load here. So what are this 120? So about point C, what is the moment is 120 multiplied by 2. 120 multiplied by 2. But because it's creating a clockwise moment, about point C, I'm going to put a negative sign here, right? And I have another negative moment here, right? Negative moment, just a concentrated negative moment, okay? And here I will just write negative 100, right? Just minus 100. Why? Because it's in the clockwise direction, right? Again, pay attention that this is not 100 times 2, right? Because this is a concentrated moment, right? It's not a concentrated force. Now from there, we can find our By value as positive 92.08 kilonewton, which means that our reaction force is upwards 92.08 kilonewton. Then we just take the summation of the forces in the y direction and we find Cy. How do we do that? We say, okay, 10 times 17, that's going to be negative, right? 10 times 17, that's my equivalent distributed load as a concentrated force going downward, so that's negative. And then minus 120, and then I have plus By, which I just found, 92.08, plus Cy, which is equal to 0. From there, I can find my Cy. Now, these two forces that I found for By and Cy, those are my concentrated forces, right, that I needed for my reactions. Now, let's continue the process. The first step always, after finding basically the second step after finding the reactions, is to find the general equation. But the question might be, where can we start from? So let's go to the previous page again. Here, again, we're going to go over this like more in the coming pages, but here, let's say we want to find although the question is asking like to also find the maximum deflection at point BC, like in BC, right? But let's say that's not the question. The only question is find the deflection and rotation at point A. And you will say, okay, let's just cut it like at point, like portion AB, right? that's what we do, right? Just cut point AB because this is the point I need, right? And again, like, why are we finding general equations for different portions? Because my loading changes, right? From A to B, I have a load, right? That I can write a general equation from A to B based on an X value. But after point B, a load is added here. A load B is added. So I cannot write a general equation. If I write a general equation here and I write a general equation here, they're going to be different because I have added a force, right? Meaning that my moment is different. My moment equation is different. Same to this portion. So I have three portions here, this portion, and this portion, right? Because of the loading conditions. Now, you might think that, okay, I can start from here and find my deflection rotation, but the problem is my compatibility conditions. I know that at point B, I have a roller, right? Or a pin. I have a pin here, okay? At points like this, I know my deflection is 0, right? Unless there's a settlement. I may consider that there's no settlement. My deflection at the supports are always 0, basically relative to the beam. Now, here, if my deflection is 0, that's one compatibility condition, right? I will say basically at a point like for this portion AB, at the end of this portion AB, I can say that my deflection is at B is equal to 0. But what is the other condition? I could say that the rotation for the right portion and left portion are the same. There's nothing really else to basically talk about, right? I only have one condition basically separate from other parts. I have like the deflection is 0 at point B for portion AB. So that's why I always, when you have a simply supported basically question and you have like overhangs and you want to find the deflection and rotation in the overhangs, you have to start from the simply supported portion anyway, right? You have to start with the simply supported portion. Doesn't matter what the question is asking, okay? You have to start with portion BC, right? From basically this pin and roller, okay? So that's what we always start. But then you'll basically understand this better when we are basically writing the compatibility conditions for portion AB. But now let's start with portion BC. So we just cut the beam here, right? Cut the beam like in an arbitrary point, right? Because we want to write a general equation. And what I did just take X from the start of support B onwards, right? Basically, I consider my X1 to be from point B to point C, right? Or from 0 to 12 meters. Okay, X1 is from 0 to 12 meters because this is my X1. You could consider X1 from support A, not support, sorry, from this point A as well, but I could just find it more like easier for myself. It's whatever you're comfortable with, but the math is a little bit easier when you're starting with like each for the portion you're finding. Just find from use it from B, okay? But it doesn't make any difference. But we have to be consistent. Now, this is my X1. 5 meters is known, right? I'm not touching like this AB portion, right? I'm not finding anything for this AB portion. I'm just finding my general equation for portion BC. So I have to find my moment equation, right? That's what I'm trying to do. Why? Again, because from my curvature equations that I'm going to use, I need my moment equation to find deflection. Now, what do I do? Just take the moment about point O. Now the question might be, why take the moment about point O? Okay, before even like going into like finding the moment itself. The main reason for taking the moment about point O is the fact that I have a shear force here, right? So whenever you cut a section here, you'll have a shear force, you have a moment, and you have axial force. For these types of I don't have any type of axial force, so I just neglect axial force here. So these two, when we have basically we cut, we get this shear force and moment, right? But the thing is, I only want to find my moment, right? I don't want to waste my time finding shear force. Okay, so for this question, like shear force is not my concern. So that's why, for example, let's say I'm going to take the moment about point B. In this case, I have to deal with M1 and V1, which are basically two unknowns, but I only need M1, which means that basically I have to find V1 at first again, right? But I don't want to do that. I don't want to waste my time. So just take moment about point O. And in that case, I don't have to deal with the moment of V1. Basically, the effect is 0. So I don't have to find V1. Okay. So always take the moment about the point you cut, right? I always name it like point O or something like that. Okay. So let's go to finding the moment. So let's start from the left side here, right? So the moment about point O. for this distributed load, I would have 10 multiplied by 5 plus x1, that's my force, multiplied by the distance divided by 2, right? x1 plus 5 divided by 2, right? x1 plus 5 divided by 2. That's a moment. Is it positive or negative? It's positive. Why? Because my counterclockwise direction is positive. I just, consider that. You can take any direction that you're comfortable with. Then we have here this force, reaction force. You see, this is why we found it reaction force. So in this case, I'm going to have 92.08 times x1, right? The moment about 0.0 in the clockwise direction, okay? The clockwise direction. So because it's in clockwise direction, I will have a negative right here, okay? And then I have the other force that's remaining is just m1, right? Which is what I'm trying to find, right? This m1 basically represents the moment at any point from B to C, right? And that's what basically section cut gives us, right? That's a very, very important usage of basically cutting the sections, right? We find the moment at any point, an arbitrary point in a section, in a portion, right? So plus m1, why is it plus again? Because it's counterclockwise. And usually what we do is just, we know the conventions. You can look at your lectures or strength of material book. That moment when you recut, the conventions moment is going to be always in the direction where it will basically create compression at the top and tension at the bottom. And shear will always basically in the clockwise kind of turning sense, right? Basically this V1 is turning clockwise. But again, I'm not going to go over that, but you can find them. And this is going to be very useful when we are drawing bending moment diagrams, but it's very good to just be consistent and draw them in these directions, right? In case you're wondering why I drew this in this direction, okay? And so this is 0. So from here, I'm just going to find my m1 based on x1, right? So I'm just finding m1 as a function of x1, right? So from here, I'm going to simplify, and as I say, my x1 is applicable from 0 to 12, right? My x1 is applicable from 0 to 12. Why? From B to C, from portion B, because I'm writing an equation for portion BC. So my basically equation is applicable from point x1 0 to x1 equal to 12, right? So I just get this and simplify this. This is my equation, right? This is my general equation from B to C. So basically, if I put x1 as 0, I'm going to basically get the moment at point B. If I put x1 12, I'm going to get the moment at point C, okay? So I'm going to use this moment equation to basically write my curvature equation and determine the compatibility conditions. So here, what is my curvature equation? It's whatever the EI is, right? Basically the stiffness multiplied by the curvature is going to give me my M1, right? And this is, you can find it in your strength of material book. This is the elastic beam theory, coming from the elastic beam theory. And of course, this is based on the assumption that our deflections are small. So this is basically a simplification has been made. So here we write our M1 that we just found, and we are going to basically integrate this 2 times, right? This is called the method of integration. So here, if we integrate this once, we're going to end up with 2EI d nu 1, and this basically this symbol is called nu, right? Nu, deflection. D nu 1 dx1 is equal to, we just integrated, right? Negative 5 divided by 3x1 to the power of 3 plus 42.08 divided by 2 x1 squared, right? Minus 125 x1 plus c1, right? These constants are the basically heart of these types of questions, right? This is what we're going to deal with. Plus c1, right? So constant of integration. And what is this? A very important point and note for us is the fact that d nu dx is theta. And we talked about this, in the method of superposition as well. And I'm going to just provide a link to that as well in case you want to check that out. And but here, basically, d nu dx, or the first derivative of my deflectional elastic curve, is going to give me my theta, right? And it makes sense, but it's a slope, right? A slope or rotation of the elastic curve. So this is theta, right? This is very important for us to understand. Later, we're going to deal with it in our calculations. And then if I take the integral of this once more, I'm going to end up with 2i nu 1 equals this, right? Again, it's just a simple integration. Plus c1 x1 plus c2, right? This is the second constant of integration. So I have 2 constants of integration, here, what are my compatibility conditions? And before going to that, we use 2EI, right? And the reason is that we had 2EI here, EI here, and EI. So essentially it means that the stiffness here is 2 times the stiffness here and here, right? That's basically what it means. We can have any value, and of course we can design based on the deflection as well. Now, for compatibility conditions, we know that at the supports, my deflection is 0, knowing that settlement is 0. So my deflection here is 0, my deflection here is 0. So when my deflection is 0, what does it mean? It means that my new one is 0. At x1, at x equals 0, and x equals 12. Right? At x equals 0, because why? My x1 is starting from 0 to 12. So as 0 is 0, and at 12, it's also 0. Which equation does it relate to? Is it 1 or 2? It's equation 2, right? Why? Because equation 1 is about rotation, or theta, right? This is not what I'm dealing with right now. My compatibility conditions are related to deflection directly. Nu 1. So nu 1 is 0 when basically at x1 equals 0 or x1 equal to 12. So I'm basically going to substitute my values here and find C1 and C2, right? Because I have 2 equations here and 2 unknowns. I can easily find my C1 and C2, right? And this is the reason we're basically starting with portion BC first, right? I can't deal with A, B like separately, right? So that's important to understand. So here I'm just going to substitute my equation, so substitute my value. So this is my basic equation. I'm going to put nu 1 0 at x1 0 and nu 1 0 and x1 at x1 12, right? So here when I put x1 0 and nu 1 0, nu 1 0, x1 0 0 0 0. So what I'm going to end up with I'm going to end up with C2 equals 0, right? It's pretty simple. But for the other compatibility condition, it was that x equals 12, at x equals 12, x equals 12, 12, 12, I'm going to have a deflection of 0. So 0 is equal to basically this. And by the way, this is, based on knowledge that C2 is 0 already. So we know that already we don't have to deal with C2 anymore. So C2 is 0. So here we didn't write C2. So from here we can find our C1. And from here you can get the C1, right? So it's positive 460.08. So here we can rewrite the equations that we had based on C1 and C2 that we know, right? So we know C1 and C2, just rewrite them, right? So this is for rotation, right? And remember, it was like d nu dx, right? I just replaced it with theta 1, right? Because, as I mentioned, the first derivative of my deflection is going to be the rotation, okay? And so this is for the rotation and this is for the deflection. And now after rewriting these, basically it means that from this point B to point C for this portion BC, I can find the deflection and rotation at any point, right? I can find the rotation and deflection at any point. So what was the question that we had? One part of the question asked us to find the maximum deflection in portion BC. So when is the deflection maximum? From calculus, we know that the deflection is maximum when my rotation is 0, when my slope is 0, right? That's finding local optima, right? So here, this is just something, again, like this, it is not completely necessary for you to find the elastic curve when you're using the method of integration. And sometimes it can be like tricky. Of course, it really helps to find the elastic curve by yourselves, but sometimes it's tricky, and this is a tricky one in case you don't know like which load could govern like from the right side or left side. But this is what the deflection basic curve is going to look like. But in reality, you really don't need to know the elastic curve for this question, right? For the method of integration. So when is deflection maximum? As we said, it's going to be when my rotation is 0. So you can see like it doesn't matter like if you have an elastic curve, it's just going to be somewhere here. My basically rotation is going to be maximum. Now what can I do? I have an equation for rotation, right? I have an equation for rotation. So rotation is going to be 0. I'm going to find my x1. I want to see what is the location where my basically rotation is 0 or deflection maximum. What is the location? So using our calculator, we're going to end up with 7.53, 2.55, 2.55. So the first thing to check here is that, okay, x1 was from 0 to 12. So sometimes you're going to end up with like negative 2.5, positive 7.8, and like 17.2. So in that case, what is my answer? My answer is definitely like that, the answer that was in the range, right? That was in the range, right? In that case, like I would have like one answer. But in this case, all these three answers basically fit in the range, right? From 0 to 12, right? So all of these could be the answers. And this case, 2.55 is like basically this is repeated 2 times, so it doesn't matter. So I'm just going to find my deflection based on my deflection equation that I had, based on this value and this value. See which one governs, right? See which one governs. So here, I'm going to basically put here 7.53, one of the answers. So I'll end up with this one, okay? And I'm going to basically put 2.55 here. I'm going to end up with this one. Which one is higher? This one, right? Again, another important point is that don't forget to divide it by 2, right? So here I found this like that, and I found the value, and then I divided it by 2 to find this, okay? Same for this one. I found this value, and then just divide by 2, right? Again, like this equation comes from the deflection equation, right? There's a deflection equation that we just found, right? We rewrote the equation in the previous page, and I just substituted the values that I found from this equation, right? From the rotation. So I just substituted 7.53 and 2.55. And of course, I'm basically looking for the larger value, right? I don't care about this one. I'm looking for the maximum deflection, and this is the maximum deflection, right? So that's for the one part of the question. Now let's move to, so here, yeah, the maximum deflection is this one. Let's move to finding the deflection and rotation at point A. So here again, we're going to cut portion AB, right? Cut portion AB. I cut it from the left because it's much easier. So if I cut it from the left, basically cut it and take the left side, I'm going to have like x2 starting from the left side, right? X2. My x2 is going to be basically from 0 to 5 meters, right? 0 to 5 meters. So here I'm going to basically take the moment about again point O, right? The formalism that we discussed. So it's going to be 10 times x2 multiplied by x2 divided by 2, right? 10 times x2 is my force. My moment is going to be x2 divided by 2, right? Because of the distance of this concentrated force from the point O. And it's going to be positive. Why? Because I just considered my counterclockwise as positive. So is there another force? No, because I'm taking the moment about point O, so V2 creates no moment. So plus M2, why is it plus M2? Because this is again in the counterclockwise direction. And from there, I'm going to end up with this, basically M2 equals negative 5x2 squared. And this equation, as I said, is applicable from 0 to 5, right? Why? Because from A to B I had 5 meters. So here I can write basically my curvature equation. This is my curvature equation. This was EI, as you remember. It was not 2EI, right? For portion AB, we had EI. And as the curvature is equal to M2, negative 5x2 squared. So we integrate once and twice, I'm going to end up with the rotation equation and the deflection equation, okay? And I just call them C3 and C4 because I already used C1 and C2, okay? So these are going to be my compatibility equations. So we already wrote the compatibility, but we already basically wrote the rotation and basically I mentioned in the previous page the compatibility conditions. Sorry, like these are the compatibility conditions. Yeah, those were basically the equations for deflection and the general equations for rotation and deflection. Here, these are the compatibility conditions. What are the compatibility conditions? The compatibility condition is, okay, we said from portion A to B. At x2 equals 5, why is x2 equals 5? Because if I want to find like support B, from the left side, I go 5 meters, right? So at point B, I can say my deflection is 0 here, right? That's pretty simple. But what is the second condition? I can say my beam is continuous, right? I have a continuous beam, right? There's no hinge, there's nothing. So because of that, I can say that my rotation at one point from the left side and right side is going to be the same, right? It's not a hinge, it's just a pin. So, and this is a continuous beam, so my rotation at this point from the left side or right side is going to be the same, right? Because it's a continuous, the beam is continuous. So theta B left is equal to theta B right, okay? This is my compatibility condition. But there's nothing really else that we can consider here, right? These are the only things we can talk about. So these are two compatibility conditions, right? And we have basically two equations and two unknowns. We can easily find C3 and C4, right? So what I always do is basically start with the value that I already know, right? Which value do I know? Do I know like theta b left? No, I have no idea because it's based on C3, right? What about this one? From this one, can I get like anything? Not really, because I have my deflection equation has like C3 and C4. You know, I can't find them directly. But what I can do, I can find theta b right? Why? Because for portion BC, I already wrote my equation, right? I know my equation already, right? And you see, like, this is why we always have to start with portion BC, with the simply supported portion. Okay, it doesn't matter what the question is asking, right? What the question is asked about, like deflection and rotation. We have to always start with the simply supported portion. Now, what do? For theta b right, we already knew our equation, right? We already know our equation. So for the theta 1 equation, right? For theta 1, so this is not about theta 2, this is not about portion AB, this is about portion BC, right? We said, okay, at point B, which is what? As x1 equals 0. At x1 equals 0. I can find my rotation, right? This is what I'm intending to do for this part. Just find this one, so just put 0, 0, 0, and just again, like 460.08 divided by 2, I'll get 230.04, right? This is my rotation for the right side of B. But I know for the left side of B, my rotation is going to be the same as that. So I would say now theta b left is going to be equal to 230.04 divided by EI. Now I can start solving for portion AB, right? I can say theta b left, which is here, right? Theta b left, so we had 5 over 3 times 5 to the power 3 plus d3. This is the equation that we had in the previous page, right? So here we are going to have this, but this basically value for theta b left, right? So the next thing we just have to do is just equal this and that, right? Because we know theta b left is equal to theta b right, as we have here. Okay. So if we equal them like that, and you know, the way we found this is just, you know, add these together, basically negative 208.33 plus C3 divided by EI. Okay, this is what theta b left is, right? So basically from here we can see that C3 is equal to 438.37, right? Because this is equal to this, okay? Now, we know C3, we can go and find our C4, right? So from here, we know that this is my equation, this is our equation for deflection, right? And what is this? This was C3, right? I just substitute C3 because I just found it, right? And then I will move, what was the next compatibility condition? It was that at B, or x2 equals 5 meters, right? x2 equals 5 meters here, my deflection was 0, right? My first condition was the rotation left, right was the same. My second condition was that my deflection is basically 0 at point B. So here it is. So here I just put x2, 5, x2, 5, C4 is going to be what? I'm going to find that. But my nu is going to be 0. My nu is 0, x2, 5, x2, 5. So I put the values like that, and from C4, for C4, I find this value, okay? So basically what I do next is just substitute the values, right? Substitute values basically for rotation and deflection. So this is my general equation for portion AB, right? For portion AB, this is my rotation and this is my deflection. How? Because, you know, this is C3, right? I know this already, right? I found it from the previous page. C4, I found it from here, right? C3, C4. Okay, so this is my equation for rotation and deflection. And what I do to find the deflection and rotation at point A is just, you know, put x2 as 0, right? Why? Because my x2 starts from the left side to the right side. So at point A, my deflection and rotation, what is the location? At x2 equals 0, right? From the left side, the rotation and deflection is at x2 equals 0, right? But what is it? So I'll just put x2 equals 0. We're going to end up with the values we want, right? So for theta A, what did I do? Put x2 0. It's going to be 438.37 divided by EI. For basically nu2, the deflection, I'm going to put again x2 0, x2 0. I'm going to end up with negative 1931.43 divided by EI. Okay, this is what we have. Okay, as simple as that. So this is the way we find our rotation and deflection. Again, let's recap. What did we do? the first step, find the reactions. Next step, basically deal with the simply supported portion BC, right? And for that, what are our compatibility conditions? The compatibility condition here, the deflection is 0, and here the deflection is 0. Basically, at x1 equals 0, the deflection is 0. At x1 equals 12, the deflection is 0, right? You can write the curvature equation, deal with the compatibility condition, easily just find the C1 and C2, rewrite the equations for the rotation and deflection, and now we have a general equation from B to C, okay? And from that, we found our maximum deflection, and where is our maximum deflection where my rotation is 0, right? And again, then we put rotation as 0, and we find the maximum deflection, right? And for the deflection and rotation at point A, we cut the portion AB here, and basically we find a moment equation, write the curvature equations. The compatibility conditions are that the deflection at point B is 0, and the rotation from the left side of B and the right side of B is going to be equal, basically. So from those, we're going to basically find our constants, right? And again, just put x2 equals 0 here to find our basically rotation and deflection at point A, okay? And that's it for this question. So if you enjoyed the video, please like and comment down below, and subscribe for more content about problem solving in structural engineering. And I hope to see you next time.